Welcome to this explainer on programming logic and design. Have you ever looked at a crazy, complex piece of software and thought, how in the world was this actually built? Well, you're absolutely in the right place. Today, we're going to break down how to build software from the absolute ground up. We're going to strip away all the confusing syntax of specific languages and just focus on the pure logic. We'll take you from the basic raw materials of code all the way up to the master blueprints, and I promise we're going to do it without getting totally overwhelmed.
Okay, let's dive into this. Because, coding actually starts way before you ever type a single line on your keyboard. It's a highly structured process known as the Program Development Lifecycle, or the PDLC. Think of it kind of like building a house. You don't just grab a hammer and start swinging wildly, right? First, you have to truly understand the exact problem you're trying to solve. Then, you plan the logic out using visual tools like flowcharts or pseudocode. It's only in phase 3 that you actually write the program, translating your logic into a language like Python or Java. After that, it's all about testing the program with real data to squash any bugs, and finally deploying and maintaining that finished product out in the real world.
To guide us through this build, here's our architectural syllabus for today's explainer. 1. Basics and building blocks. 2. Logic, decisions, and control. 3. The power of loops. 4. Managing data with arrays. And 5. Modules and object-oriented programming.
So, moving right into Section 1, Basics and Building Blocks, the raw materials of code.
The absolute most fundamental building block in programming is the variable. A variable is simply a named storage location in your computer's memory, used to hold data that can change while the program is running. Think of it as a container, or like a labeled box. But to create this box, you've got to follow some pretty strict naming conventions. The universal rules are that your label almost always has to start with a letter, you can literally never use spaces, and you should always make it descriptive, something like student name or total cost. Building on that, you have to tell those variables exactly what kind of data they're holding. Broadly speaking, we have numeric values and string values. Numeric values are your integers and floating point numbers, the stuff you're going to use for actual math calculations. String values, on the other hand, are just sequences of characters. It's essentially text, like the word hello, or even a sequence like 1, 2, 3, 4 if it's saved as text. Now, a classic beginner trap is trying to do math with a string. If you store the number 5 as a string, the computer just sees a text character. It's not a value it can multiply or divide, so your program will just throw an error.
So the crucial point here is understanding the fundamental difference between variables, which obviously change, and constants, which are named values that absolutely never change during program execution. Think of the mathematical value of pi. You definitely do not want that accidentally changing halfway through your program. Using constants also saves us from this terrible coding habit. Actually, it's more of a rookie mistake, called using magic numbers. A magic number is just a hard-coded random literal number dropped into your code with zero explanation. By replacing that random number with a cleanly named constant like max_users, your code becomes instantly clearer and just so much safer to manage.
All right, Section 2, Logic, Decisions, and Control, Directing Traffic.
At the very heart of computer decision-making is this brilliant concept developed by a 19th century mathematician named George Boole, the Boolean expression. It's an expression that evaluates to simply true or false. There's no maybe in programming. This true or false binary is the foundational heartbeat driving all our control structures, like if-then statements. If the user's age is greater than or equal to 18, then output adult, else output minor. Every single decision ultimately boils down to a true or false evaluation.
Now, what's really interesting about this slide is this is basically your ultimate quick reference cheat sheet for the operators that power all that logic. We have relational operators, which just compare two operands. Is this equal to that? Is this less than that? And then we have logical operators, and, or, and not. These are awesome because they allow us to string multiple conditions together, like if age is greater than 18 and score is greater than 50. But keep in mind, these operators have strict precedence rules, just like in regular math equations. The not operator takes the absolute highest priority, followed by and then or. Honestly, using parentheses is always your best bet to keep complex expressions super clear and guarantee the computer evaluates them in the exact order you want.
Let's move to Section 3, the power of loops, doing the heavy lifting.
Listen, in programming, if you find yourself writing the exact same line of code over and over again, you are definitely doing it wrong. Loops are how we get the computer to do all the heavy lifting for us. There are 3 main types of repetition structures, or loops, that you really need in your toolkit. First is the while loop, which repeats a block of code strictly as long as a condition remains true. Second is the do-while loop. The cool, unique thing here is that it guarantees the code executes at least one single time before it even bothers to check the condition. And third, the for loop, which is absolutely perfect for when you know the exact number of times you want to repeat something, like counting from 1 to 5. But I've got to give you a proactive warning right now. Always make sure your loop control variable updates correctly. A super common beginner trap is accidentally creating an infinite loop. That's where you use the wrong condition, it never becomes false, and your program just gets stuck repeating forever until the whole thing crashes.
Okay, Section 4, Managing Data with Arrays. Warehouse Storage.
Think about this for a second. If you needed to write a program to store the test scores for, say, 100 students, would you really sit there and write out 100 separate variables? No way. That would be a complete nightmare to manage. The elegant solution to our 100-student problem is an array. An array is just a collection of elements of the exact same data type, all neatly stored under a single variable name. Imagine a really long row of post office boxes. They all share one street address, which is the array's name, but each individual box can hold a different piece of data. The only catch is that in an array, all those pieces of data must be of the identical type. So they gotta be all integers or all strings. You literally can't mix and match.
Now, I've got a crucial question for you to test your intuition on how we count items in programming logic. If you want to open the very first box in that row, if you want to access the very first item in an array collection, what number do you use to ask the computer for it?
The answer is 0. Yeah, programming indexing almost always starts at 0. So if you want the first test score, you actually ask for the item at index 0. If you have an array of 5 items, their index numbers are 0, 1, 2, 3, and 4. Forgetting this incredibly simple rule is exactly what causes the dreaded out-of-bounds error. That happens when you ask the computer for index 5 in a 5-item array. That index simply doesn't exist, and boom, your program breaks.
Once your data is all neatly tucked inside an array, you're often going to need to organize it. One foundational way to do this is the bubble sort algorithm. The mechanism here is just beautifully simple. First, you loop through the array. Second, you compare 2 adjacent values right side by side. Third, if they're out of order, like say a 9 is sitting in front of a 2, you just swap them. And fourth, you repeat this whole looping and swapping process until no more swaps are needed. The larger numbers literally bubble up to the very end of the array until the whole thing is perfectly sorted.
And that brings us to Section 5, Modules and Object-Oriented Programming, the Master Blueprints.
We've covered a ton of ground, and now it's time to look at how we build massive, highly complex applications without totally losing our mind. As your programs get bigger, you can't just write one giant scrolling list of instructions. You have to break things down. Enter the module. A module, which is also commonly called a function, a method, or a procedure, depending on your language, is a self-contained, reusable block of code designed to do one highly specific task. Instead of writing the math to calculate taxes in 5 different places, you write one calculate tax module. Then your program's mainline logic just calls that module whenever it needs it. This drastically cuts down on redundancy and makes testing and debugging so much easier.
You can even take it a step further with what we call overloaded methods. Overloaded methods are methods that share the exact same name, but they accept a different number or a completely different type of parameters, which are just the inputs you feed into the module. So you could have a method called print that specifically handles a string of text, and another method also called print that handles an integer. The computer dynamically knows exactly which blueprint to use based entirely on what kind of data you hand it. It's pretty smart.
Taking this whole concept of reusable design to its absolute peak brings us to object-oriented programming, or OOP. To really grasp OOP, you have to understand the relationship between a class and an object. A class is purely a blueprint. It just defines the attributes and methods a thing should have. An object is the actual, usable instance built directly from that class blueprint. For example, student is the class blueprint. It says every student has a name and an age. But the actual data representing you, the viewer, that is the physical object built from the blueprint.
And this brilliantly illustrates the 3 core pillars that give object-oriented programming its incredible scaling power. First is encapsulation, which simply means protecting the object's internal data from outside interference, basically putting a protective shell right around it. Second is inheritance, where a new child class can automatically inherit attributes and methods from an existing parent class, which saves just massive amounts of coding time. And third is polymorphism, this really powerful concept meaning methods with the exact same name can actually behave differently based on the specific context of the object using them.
Well, we've journeyed all the way from the raw materials of basic variables, through the traffic control of Boolean logic and loops, all the way up to the towering architectural master blueprints of object-oriented programming. You've really seen the logic behind the code. So now that you have the basic blocks in the master blueprints, what complex, real-world problem will you build a solution for first? The tools are all right here, just waiting for you. Thanks for joining me on this explainer, and as always, stay curious.